Hello, everyone. I want to introduce myself. My name is Eric Glenn, and I am the Program Manager for Safety. We appreciate you joining the webinar on driver risk assessment based on high frequency, high resolution telematics data. You have all come into the meeting muted, and we would appreciate if you stayed muted until the Q&A session. If you have any questions during the webinar, please type them into the chat box, and they will be addressed at the end. I'd also like to point out that Dr. Fong Guo has also put a couple of messages for everybody in there. I believe the web app is in there along with 2 papers. At this time, I'd like to introduce the presenter. Dr. Fong Guo is a professor of the Department of Statistics at Virginia Tech and a lead data scientist at Virginia Tech Transportation Institute. Dr. Guo actively engaged in both methodology and practice research on quantitative transportation modeling, especially in traffic safety assessment. His major research areas include analysis of naturalistic driving studies, transportation infrastructure, safety evaluation, advanced vehicle proactive safety device evaluation, and automated driving systems. Dr. Guo has served as the chair of the Transportation Statistics Interest Group of America, Statistical Association, a member of the Transportation Research Board Committee on Statistical Methods, and a member of the Committee on Safety Data Analysis and Evaluation. Dr. Guo has been a principal investigator and co-principal investigator for more than 50 research projects sponsored by industry, federal, and state agencies, including the FHWA, NHWSA, FMCSA, and CDC, along with the UTC that we have here. Now that the introductions are complete, I will turn it over to Dr. Guo.
All right, Eric, thanks for the nice introduction. Thanks to everybody for joining this webinar. So I will, let me see. All right. So I'll talk about one of our UTC project, driving assessment, use high frequency, high resolution kinematic data. So this is a joint work with my students, Chen Qian, Liang Shi, and also our collaborator, Dr. Chen-Yang Chao from Duke University. So traffic crash are a leading cause of death worldwide, 1.35 million fatalities annually. It's the leading killer of the people, especially for young people, 5 to 29 years old. So crash typically is a gold standard in safety evaluation, but they are also very rare. For a regular driver, we typically take out 5,000 years to experience a fatal crash, 30 years to experience a police reportable crash or for an individual driver. So this rarity of crash causes a lot of challenges in safety evaluation, prediction. One of the famous random report basically saying, if you like to confirm automatic driving systems are safer in terms of fatalities compared to human drivers, at our current pace, we need to do data collection for 250 years. Right? So rarity of the crash is a main issue. Traditionally, crash risk assessment and prediction, especially prediction at aggregate level, for example, age, past crash history, and traffic violations. So in heavy safety manual approach, the infrastructure characteristics, driving environment, they are typically the main predictor for this. The challenge with all these traditional predictors are, first, they are sparse as well. Like crash is rare. Traffic violations, you would think there's a lot of them, but based on our experience, only a few traffic violators actually got ticket. So the traffic violation record actually even sparser compared to crash. Infrastructure, typically you deal with a fixed location. So all these either too coarse or too rare. So in recent years, high frequency, high resolution driving data became almost ubiquitous available. Large-scale naturalist driving study, those onboard monitoring system, some of the industry leaders like Smart Drive Analytics, they collect tons of this data using onboard systems, smartphone apps, Google Map navigation, Apple Map, Waze, they can all collect this kinematic information, let alone the connected vehicle ADS. They are connected by nature, right? So you do collect all this critical high resolution driving data. So the challenge for us is how do we use this data? Use one example, the kind of area that most people are familiar with this, the SHOP2. So we have 34,000 drivers, 1 million hours of continuous multivariate high frequency data, radar, multi-cameras, three-dimensional accelerations. But out of all this, we got about 2,000 crashes. Only a couple of them are severe crashes. So it's big data. It has the typical characteristics of a big data issue. It's massive streaming type of data. It's high dimensional multivariate, but they are very noisy. So to be able to extract useful information from this massive amount of driving data is the main challenge. So that's one of our main goal of this project is how to efficiently use this continuous driving data to improve safety. And more important, more specifically, can we distinguish safety critical event from normal drivings using the just kinematics data in real time? So we propose two approaches to address this problem. First is it's a fancy name for machine learning, but this is a full neural network model. And the second one is a little bit more traditional approach, use variational inference for extreme to handle the rarity of the crash. So the first one is based on raw data. We feed all the raw data into the model, and it will give us the probability of crash or near crash. Second approach is based on feature engineering. We developed some fancier driving robustness, driving condition robustness index, and we developed a variational inference model for rare events. So for the first approach, okay, so the data we used are SHOP2 and DS. So here we use the full entirety of the SHOP2 safety critical event. We have about 1,800 crashes and close to 7,000 near crashes. And it's fairly easy if you just do a fair comparison. If you go to Insight to download the driving segment and compare with crash, near crash, it's fairly easy because the crash or near crash typically involving some speed reduction. So in order to make this more realistic and more applicable in real life, we actually find matched normal driving segments. By matching, we're matching the maximum and the minimum speed of a crash and near crash. Okay, these are all based on about 30 seconds window, and we use the same driver. So they try to eliminate the different driving style, individual driver effect out of this. So each event eventually we took 5.1 seconds long, but the raw data we have about 30 seconds. So variable we evaluate include speed, three-dimensional acceleration, and yaw rate. So the goal is to distinguish the three types of events. So to train the model, we first like to find the segment with key signals. And by key signals for each of the crash, there is a part of the driving that represent the key driving kinematic signatures of a crash. So in that case, what we did is we calculate the horizontal acceleration. So this includes both longitudinal and lateral. And then we sort of look at the entire segment and try to find the part, use 5-second moving window to identify the time stand with the maximum variance. And then we got this for the crashes, and we do similar things for the normal drivings. So 5-second window, continuous 10 Hertz data give us about 50 data points. Okay, so we use this to test to train the model. The modeling included two different parts. The first part is the full neural network model. Okay, so main part for both approaches, they have a kind of feature engineering component and a classification component. The more tricky part is the feature engineering part. So we use a full neural network model, and for the classification part, one model use XG boosting, just because this is a pretty big data set, but they are relatively small if you look at all these big full neural network model trainings. So we compared these two classifiers. So the feature engineering part, we have three main layers. One is the convolutional neural network layer. Second one is a maximum pooling layer. And third one is the gated recurrent unit layer. So essentially a long short memory layer. So the reason we have these three layers is each one of them serve different purpose. For convolutional neural network models, we're trying to characterize in the local spatial informations, right? So if you look at a crash, kinematic of the crash, there are some patterns we're trying to catch that. Those can be catched locally. And CNN traditionally, they are used with image processing. So just factor the spatial correlation among adjacent pixels. So we borrow the similar concept in this kinematic time series data context. So each data point adjacent to each other, they are correlated with each other because of the temporal correlation. And we're trying to use the CNN to extract these local informations. And you sort of can see that effect here. This is the on the left, lower left corner is the output of the CNN. So you can see the first part output. Remember, like when we're doing the training data, we sort of find the maximum, the sections with the maximum variance. So the largest acceleration or kinematic variation actually happened around the middle of that. So prior to the critical moment, their correlation among the observations are high. And after that, they are high. In the middle, because you have this big jump, so the spatial correlations actually are a little bit smaller. So CNN is used to capture this localized characteristics. And we do a maximum pooling just to integrate based on extreme values. And then once we have this CNN output, put that into a GRU. GRU is gated recurrent event unit. It's one type of long short memory model just to further incorporate the spatial correlations among observations. It's commonly used on natural language processing. So by combining this different type of neural network models, we're trying to capture the key characteristics of the kinematic signatures and trying to use those output. Two purposes. One is to extract useful information. Secondly, we're trying to reduce the impact of noise and random fluctuations. And here are some more details about technical details. Instead of use the common rule activation function, we use a tangent H function. So it's just our data size is not that big. So the diminish of gradient is not a big issue. And the tan-H activation function gave us a little better results. So here are a little bit more detailed full neural network setups. So for the data, we have N is the number of sample size. So we have a 5-second window, 10 Hertz. So we have 50, each event has 51 seconds of that, 51 data points at different timestamps. And we have 3-dimensional acceleration. So we have tensor of N times 51 times 3. So we put into the first layer of convolutional neural network, so sort of doing a reduction, 3-level reduction, and we do maximum pooling, and then put that into a GRU, and then we put into a weighted network just to take care of the imbalance in the data, weighted penalty network. and doing a batch normalization, and eventually put that into a classifier. Use a softmax output layers. So we have 3 types of events: crash, near crash, and baseline. And then we use this to do prediction. The second approach has similar structures, but instead of using a full connected neural network, use the XG boosting classifier. So all the feature extracted from the first 2 layers put into XG boosting, XG booster classifier. So it has a little bit less data requirement compared to a full neural network model. And in terms of performance on testing data set, the XG booster classifier actually gave us a slightly better performance. One of the most important, if this success or not, it depends on if we can distinguish normal driving, crash, near crash at latent space. So we compare our model with some of the current benchmark models. So essentially, if we did a good job from this type of plot at latent representations, crash, near crash, and the normal driving behaviors, they should be separate from each other. So you can just by looking at this, the left up corner is our model. You can see the red is crash, yellow is near crash, and light gray is the normal driving behaviors. Especially for crash is our model in terms of distinguish, give a better representation at latent space, give a better results compared to other benchmark models. Okay. So here a little bit more quantified access model in terms of the recall rate. Just use raw data. We can recall about 72% of the total event. Accuracy altogether is 97.5%. Okay, so it is decent, but we can further. So here you can look at one of the more important kind of index I'm very interested in is the false positive rate. So if we predict this as crash, how many of them are actually crash? The issue with a lot of this rare event modeling is the identify false positive rate is too high. Among the predicted events, they're gonna be overwhelmed by false alarm. But in this model, we can see for all the predicted crashes, 82% of them are actually crash. Right, so only less than 10% of them are normal driving. So we are pretty happy with this model performance in terms of false positive rate. Okay, so in order to further and put it in more like realistic actual application perspective, I mean, in real life, it's difficult to first try 5-second window, find the maximum disturbance part, and then apply a model. So most likely scenario, we are dealing with streaming data. So we are actually use window to scan through the entire data set in order to find that. So that's actually when we're doing the application, we use this approach. So use 5-second moving window, it's continuous scan of the entire data. And then we, at each time point, we output one probability: crash, near crash, or normal driving. So here are some of the results. Okay, once you do that, in the lower right corner, you can see the model output. This will also be in the web applications. So the red color means the probability of the crash. Yellow means the probability of the near crash. And then 3 lines we have longitudinal, lateral, and vertical accelerations. So once you do a moving window type scanning, what you will get is you will get a continuous probability at each data point. So to distinguish if this is crash or not, we use a bagging technique. So essentially, this is a little bit arbitrary. I think in the future, there's a room for improvement. But if you say, okay, here we detect there's a crash, but I will not take a single output as it is because there's a lot of noises with it, right? In order to call it a crash, I will at least have 10 consecutive windows indicate the probability of crash is larger than 50%. After impose this constraint, our recall rate for the most severe crashes are 99%. Police reportable crash are 91%, minor crash 80%, and low risk tire strikes 85%. So remember, the overall recall percentage without this bagging approach is about 72%. So the bagging really increased the model performance. Okay, so I will do a little bit I will do a little bit demonstration with this web tool. Let me share this window. Okay, Erica, can you confirm you see the website?
I can confirm the website is on and we can see it.
So there's linking to the project site. So this is give you a little bit of background information, the project team. Our final report going to be posted here. But let's go back to this. So there's two tabs. One is demo, use our sample data, and you can also upload your data to try this model. Let's see a few examples. So this is actually done in real time. This website computing power is not that huge, but it can still handle this calculation no problem. So in real time application prediction, I think this is up to the task, very efficient. So here in this interface, you can see on the top what we talk about. So left is the G-force acceleration. Okay, 1G is 9.8 meters per second square. And on the right side is the probability of crash and a near crash. If they are not crash, near crash, they are normal driving. So you can see all the add up to 1. So at each data point, you can see the value of longitudinal acceleration, lateral acceleration, vertical accelerations, the probability of crash, and the probability of near crash. Right? So you can see if we do a scanning, of course, you sort of need about 2.5 seconds prior to that. Once we get to that, the probability of crash kind of fluctuate a little bit, but in general, very small. And then once you get to this big disturbance part, you can see the probability of crash is 97%. All right, so around this entire region, the probability 0.999 is we're pretty positive this is a crash. Okay, so and because the vertical acceleration has one natural gravity acceleration in that direction, so you can sort of see the lateral are larger than the vertical. If you like to see them on the scale, you can push this button. It will adjust the 3 acceleration. Basically, get rid of the 1G of gravity force from data. Okay, so the app also allows you to look at through the entire process to see exactly what kind of features are affecting crash. Right. So here's a window, 5-second window. So if you move that, you can see the corresponding fluctuations in crash, near crash values, and also the acceleration values you can see here. So you do have a sort of almost 0.2 G longitudinal acceleration, but the probability of crash is fairly low. I mean, 0.2 G is pretty normal braking force. And once you get to the this part, you can see the probability of crash sort of increased dramatically, right? So this is very sure. Okay, so and also you notice among the longitudinal lateral accelerations, little fluctuations. It's very interesting. During crash, the vertical accelerations also have a spike. So our theory is during a crash, because the vehicle impact another object or even roll over. So typically, during a normal, even near crash situation, you will not register a vertical acceleration. But during a crash situation, this vertical acceleration become critical, one of the critical elements in that. Okay. So yeah, this allows you to sort of go through the entire process and to see exactly what make this this particular segment with high probability of risk. All right, so we can use a near crash. Let's look at the near crash situation. So here is the near crash, and we normalize this, as you can see. So one of the main sort of big difference compared to the crash situation. So here is big. So you can see here, you have 0.8 g, okay? You have a 0.8 g longitudinal acceleration, but itself, okay, only indicate it has a higher probability of a near crash instead of crash. So compared to the previous example, the main difference really actually is on the lateral acceleration and vertical acceleration parts, right? So yeah, so that's give you micro level, and here you gave like 3 windows, right? So prior to the current window, what is the probability of crash, probability of near crash, and normal driving, current and previous and the next, can sort of how it evolve. And this is the near crash, although at some point it's sort of, hey, you know, this is more likely to be a crash, all right? But it lasts only very short time and then become a dominant near crash situation. So this is another demonstration of the bagging, power of bagging, right? Normal driving is typically, you can see the performance are pretty stable. I mean, at some point you will notice there is a slightly chance of crash, but they are really small compared to the actual events. Okay, and also you can upload your data after the. I will post the data format later on the website as well. So if you like to try your own data, you can upload your data to the file, and it will do exactly similar situation. So what we did here is we actually load all the data. All the calculation is actually in real time. Okay. Now go back to the next part. The next part is a little more theoretical. Sorry, I have to mention this is our graduate student Liang Shi. He is one of the computer engineers, can design all this website and doing coding, deploy all these fancier machine learning models. So the next part is a little more theoretical. So we are dealing with the situation to predict severe crashes from normal driving. So in this case, we did not take all the data. We just select 78 crashes and about 30,000 near non-crash normal driving segments. So again, we match the initial and ending speed. So the number of events are much smaller compared to normal driving. So we try to develop a statistical model that can accommodate or handle this severe imbalanced data situation. Instead of using all the features extracted using machine learning, in this approach, we take a different approach. So the feature is based on domain knowledge. So if you look at all this high kinematic data, you have maximum, you have mean, you have minimum, you have variance, and you can use Fourier transformation, you can use a lot of different autocorrelation, quantiles. All this represent some key characteristics of this high frequency data set. So we, instead of using neural network, we use domain knowledge combined with engineering knowledge, trying to extract the kinematic informations, the key features from this data set. So one of the most common used event is the high G-force event. So the general idea is this, you know, normal driving will not typically go beyond 0.3, 0.4 G. So if you have a super large acceleration, deceleration means something's not right. Typically, it's because of distraction, you have late response, because the traffic is really congested, a lot of turbulence in traffic, force you to have a lot of hard brakes. So the high G-force event typically represent high-risk situation. One of the problems is what is the optimal threshold? Again, this is one of the previous projects we did under UTC, sponsored by UTC, Safety UTC as well. I list the paper here. This is an open access paper, so you don't need a subscription to read the entire paper. So the general idea is if you push to the left, the the like 0.3G, you're going to have 3.6 million high G-force event from sharp 2. If you increase that to 0.65, close to more than 65, you only have a few thousand left. So the question becomes, what is the optimal threshold? Because if you put the threshold to the left, the signal going to be overwhelmed by the noise, normal driving behavior. But if you push too far to the right, it will the high G-force event itself become a rare event. Then you basically lose the advantage of power in prediction, right? So we basically looking to test the different thresholds. So in this paper, and then our main finding is based on different applications, the threshold could vary. And you really look at really look at your research objective and develop a more systematic approach to select the optimal threshold. Well, but in general, this paper basically suggests about 0.46. If you are blind, let's say, I have to pick one, right? So that seems to be a sweet spot. So in this project, we sort of push this a little bit further. So in traffic flow theories, the vehicle dynamics derivative of the speed actually is acceleration. So if you look at transportation flow, traffic flow literatures, this vehicle dynamics, actually you can attribute it to several components. The first one is the expected vehicle dynamic due to traffic or environment. There's a big random fluctuation component. So I think what's missing is from this a jumping process, right? During an evasive maneuver, during a near crash situation, they will typically not follow this expectation or random fluctuation. There's something different, the jumping process. So based on this differential equation, we call it driving conditional robustity index. We sort of solve this. We find that this DCR has a lot of advantages, less strict assumptions, compared to, say, volatility is basically standard deviation variance used in the previous research. They are very susceptible to correlated data, but all the kinematic data are highly correlated. So data already have a built-in bias, but this DCR is very robust for that. It's suitable for heavy-tailed data and support distributed computing with theoretical guarantees. And also, it's because of this framework, it's actually reflect the underlying traffic characteristics. And of course, to put into practice, there's a lot of mathematicals. Graduate student Chen Chen, he did a lot of theoretical derivations to show the convergency properties and efficiency of those new index. And one of the best things about this is it can support parallel large-scale calculations. So you can actually do what we call divide and conquer approach. When you have massive amount of data, stream kinematic data, you can actually chop them into different small chunks and combine together to get DCR. We basically theoretically show this will converge to the cracked matrix. So this, we apply this to one of the previous DD project. Every day you get 7 terabytes of continuous driving data, and the typical traditional method will not fly. But here with DCR, it actually works beautifully. All right. Now with this extracted features, how do we use them to do prediction? And especially since we have severe unbalanced data, crash, we are looking at 100 crash with 30,000 non-crash normal driving situations. Typical logistic regression on neural network is performance on this severe imbalanced data is very poor. All right. So in order to address that issue, we put that into a variational inference framework where we put the input features and labels into a encoder. All right. So it's again, we already extract features, but we further put that into a encoder. It's essentially a neural network. And the goal is trying to get a latent representation of this data. Okay. So this latent representation, again, the goal is to now, like, suppose you got 70, we can get, like, typically we get 70, 80 features from this kinematic data. You can put that into the network, but it's no guarantee you can separate them. So the goal is to have a clear separation of the crash and random drivings in a latent space. Like, look at here, I can directly draw a line here and separate the crash and normal driving perfectly. Okay. By the way, this is actually the real data. So once you have this, everything becomes relatively easy. And now once you have that, then you like to do prediction. And in order to do prediction, again, the rarity of the model become a big issue. So if you put that into a regular decoder, full connected network, it's just too much flexibilities. So what we did is we put a monotonic additive neural network model in the decoder part. Okay, so this monotonic additive neural network is monotonic increase or decrease. And because this constraints actually solve that overfitting issues for rare event, and it works very well. So yeah, and that's one of the contributions. The other one is how do we deal with this? Is we put a heavy-tailed prior into the model. Okay, so the general idea is typically if you put a Gaussian normal prior, that's the most common one. But when you have rare event, we are actually looking at the tail part. Right? On this tail part, normal just converge to 0 too fast. Okay, so here like black is our typical. If you use a normal prior, this is what happened. All right, but we have some observations. Based on normal, you will see there's 0 probability they're going to happen here. But if this is what we are really interested, how do we deal with that? And you can do a kernel density estimator, but because the data is sparse, rare event, right? So you get a really bumpy observations. Use our extreme value prior, we actually can accommodate this. So in a simulation study, the ground truth and our EVT model actually fit very well. Okay, so here are some informations about the decoder, monotonic additive neural network models, where by impose this monotonicity, we can reduce the overfitting issues for the rare event. And this additive decomposition encourage this entanglement representation. All right, so again, we compare this with other benchmark models where we have this VIE model here. You can clearly see the normal driving and the crashes. There's clear separation between them. We compare this with other benchmark models. Again, this model seems has the best performance in terms of predict the crashes from this imbalanced data. And also the model is pretty robust. We actually put artificial noise settings to train the model. So the model, if you have noise in the data, this model can handle that as well. So we did do a quantitative model comparison, and our models beat the benchmark models in majority of the cases. Okay. In summary, with the telematic system, connected automated driving system, and smartphone apps, collecting kinematic driving data is become cheaper and cheaper by days and massively available, right? So but the rare and critical information is often hidden in the very noisy big data, right? So we typically, historically, we do not have a lot of good tools to deal with that. They are either too simple or cannot handle the mass amount of data. So the like high G-force event is one of the most popular ones. It's very efficient. You just set a threshold, you can find it, but it's very sensitive to outliers. From the naturalist driving data, we observe tons of situations where you have a instrument malfunction. You got a single spike of 1.7 G. Event data is constantly over there. You can do some smoothing, but it will not solve that problem fundamentally. So this line of work, we are hoping to go beyond this traditional simple high G-force event to capture how a safety critical event differs from the rest of the normal driving, like stop before a stop sign. And this project, what we did is we sort of pushing in very similar situations. You will go from 35 miles to a stop. Could because of there is crash, could because it's stop before a traffic signal, right? So acceleration patterns are over there, but there's a lot of hidden kind of gems and critical informations it's very difficult to extract from this massive amount of data. So what we proposed here, the deep learning model and variational inference deal with these two critical challenges. One is how do you deal with massive amount of data? How do you efficiently extract critical information related to safety? And secondly, how to deal with severe unbalanced data because the crash are rare, right? So if you design algorithm can catch a lot of crashes, but at the same time, if you give too many false alarms, false positives, people lost trust in the system. Eventually, you're going to be overwhelmed by this non-crash or non-safety critical event data. So these two aspects are the primary goal of this project, and we are hoping like this can help with pushing forward how to in the future push forward for. There's a lot of applications you can automatically detect crashes used in emergency response situation. You can estimate, evaluate the infrastructure safety, identify hotspot. You can do use-based inference based on this because of the relative high frequency of this kinematic signature event will tell you a lot before a crash actually happens. So I think there's a lot of future research direction we can also push forward. Our immediate future is now we have this rare event modeling and neural network based feature extraction. We are considering combine these two together. There's quite some in recent years. There's quite a lot of new research development in neural network modeling. We like to incorporate that. And I also firmly believe that the traditional statistical models with their highly transparent model structure, if we can find the sweet spot combined with the statistical models, will give you much more power in terms of model interpretability and other applications. Okay, that's all I have.